Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical aspects to the most practical ones. So if this is the first video that you're watching, or if you're interested in epoxy resins, please like and subscribe to our channel for more videos.
Today, I am going to present solid, liquid, and solution epoxy resins. Epoxy resins can be classified based on different aspects. This classification can be based on their chemistry or the applications. One common classification can be based on their physical state. Generally speaking, it is common to classify epoxy resins based on their physical state. Herein, the epoxy resins are classified into solid epoxy resins, liquid epoxy resins, and solution epoxy resins. Solution epoxy resins are often solid resins which have a solvent or diluent with them. The solution epoxy resins might also be referred to as modified epoxy systems. Here we start the discussion with the solid-state epoxy resins. As the name implies, solid epoxy resins are often medium to high molecular weight solids. Different chemistries can be found under solid epoxy resins. These classes include bisphenol A-based epoxy resins, bisphenol A-F epoxies, or bisphenol F resins, and also Novolac or Novolac bisphenol blend resins. Solid epoxy resins portfolio is relatively rich. Concerning the appearance, these resins can be supplied in powder form, granular, flakes, semi-solid, fused, etc. They can be provided in a clear to pale yellow or even dark yellow colors. The color is presented in the TDS documents based on APHA or the Gardner scale and is dependent on the type and the grade of the resin. As these resins are solid, the viscosity of these resins is presented as a solution of 40% in butyl carbitol as a solvent. Moreover, the flash point of these resins is often about 200 centigrade, and so these resins are not considered as flammables. The density of these resins is dependent on the chemical structure, but roughly it lies between 1.1 to 1.2 gram per cubic centimeters. Often solid epoxy resins are classified in 9 different types, type 1 to type 9. The higher the type, the solid epoxy resins, the higher weight per epoxy or gram per equivalent, and the higher molecular weight. So higher type, for example, type 8 epoxies also possess higher molecular weight. Type 1 bisphenol A epoxy resins are solid epoxy resins with EEW in range of almost 400 to 600 gram per equivalent. Type 1 resins are typically used in anti-corrosive primers and finishes. These epoxy resins may agglomerate if stored at high temperatures. They also can be designed to improve the flexibility and impact resistance of the fusion-bounded coatings. The solution viscosity of type 1 resin is around 250 millipascal second at 25 centigrade. Type 2 solid epoxy resins render an EEW of about 600 to 700 gram per equivalent and can be used for various applications. For example, to formulate solvent-based anti-corrosive primers and finishes in powder coatings with improved flow. The solution viscosity of type 2 resin is higher than type 1 epoxy resin, which is the whole trend here, and it is around 300 to 350 millipascal second at 25 centigrade. Regarding the solution viscosity, when the type is increased, the viscosity is also increasing. And for example, for type 5, the viscosity is around 1000 millipascal second at 25 centigrade. And for type 9 resins, the viscosity can reach 7000 millipascal second at 25 centigrade. Regarding EEW values also, we see the same trend, whereas the EEW of type 1 resin is around 500 gram per equivalent, the EEW of type 5 epoxy resin is around 1000, and for type 9 resin it can exceed 3000 gram per equivalent. Therefore, as a rule of thumb, as the resin gets heavier and less reactive, its molecular weight and its type is also increased. Different resin types are suitable for different applications, and therefore the type of the employed resin is determined by the certain needs. The amount of hardener is determined based on EW of the epoxy resin. The TDS document of solid epoxy resins also conveys similar information as explained in the former sessions. However, in the TDS documents of liquid epoxy resins, other pieces of information have to be presented, which will be explained here. The first feature is solution viscosity for solid epoxy resins. It has been explained that as the state of these resins is solid, it is not possible to report a viscosity for them. However, their molecular weight differs substantially. For the case of solid epoxy resins, the viscosity of a certain solution of the epoxy will be calculated and reported. This viscosity is reported based on ISO 120-58/1 standard, where instead of the sole viscosity of the resin, the viscosity of a solution of 40% resin in butyl carbitol is reported at 25 centigrade. This viscosity is a pointer to the molecular size of the resin, and so a higher viscosity often implies a higher molecular weight. The melt viscosity of a polymer at given temperature is a measure of the rate at which chains can move relative to each other. In this method, a sample of the solid epoxy is melted and put into special capillary tubes, for example glass viscometer, for viscosity measurements, where certain pressure is applied and the volume of the resin passed through an orifice in a certain time is measured and reported. It is also sometimes presented in the TDS. However, the solution viscosity is more common in this regard. It should be mentioned that the melting viscosity is intended to be lower, and lower melt viscosity the better solid epoxy. To report this property, ISO 11443 standard can be employed. The softening point of a solid epoxy can be defined as the temperature at which this material further softens after its arbitrary softening point is reached. There are various methods that are helpful in determining the softening point of a material. They are as follows: Wickett method as per ASTM D1525 or ISO 306, heat deflection test method as per ASTM D648, ring and bowl method as per ASTM E2868 or ASTM E2899. Solid epoxy resin can be used in many applications. Epoxy powder coatings are chosen by diverse industries for a wide range of applications, including architectural, agricultural equipment, automotive, manufacturing, home and office appliances, control panels, oil and gas pipelines, etc. Most solid epoxy resins offer excellent adhesion, mechanical properties, electrical properties, and resistance to chemical and corrosion, especially for metal substrate. Based on the application, EEW in range of 600 to 1500 can be used. Curing agents usually used are phenolics, disandiamide, and carboxyl terminated polyesters. Fusion bonded epoxy coating, also known as fusion bound epoxy powder coating and commonly referred to as FBE coating, is an epoxy based powder coating that is widely used to protect steel pipe used in pipeline construction from corrosion. It is also commonly used to protect reinforcing bars and on a wide variety of piping connections, valves, etc. The resin and the hardener components in the dry powder FBE stock remains unreacted at normal storage conditions. At typical coating applications, temperatures usually in the range of 180 to 250 centigrades, the contents of the powder melts and transfer to a liquid form. The liquid FBE film wets and flows onto the steel surface on which it is applied and soon becomes a solid coating by chemical cross-linking assisted by heat. This process is known as fusion bonding. The chemical cross-linking reaction taking place in this case is irreversible. The FVE powder coating application has three essential stages. The steel surface is truly cleaned. Second, the cleaned metal part is heated to the recommended FVE powder application temperature. And three, the application and curing stage. Can coating is very critical in preventing food ingredients from corroding the can's inner metal surface, as well as preventing the migration of metal ions into food items. It also helps avoid cloudiness in beverages and staining of foods. Coatings must be flexible to withstand can making operation and resist wide temperature range over long duration while adhesion remains intact. It should withstand aggressive food types without leaching and should preserve appearances and organoleptic properties. Epoxy can coating, with its high flexibility and unmatched range of advantages, has been the go-to solution for can manufacturers. Based on bisphenol A epoxy can coating, when cured by solvent removal, oxidation, or heat polymerization, cross-linking reactions from a three-dimensional network to deliver final coating properties. Typical curing agents used are phenol-formaldehyde resin and different types of amino resins. Some applications may need multiple coating layers to overcome low adhesion of the metal, secure high protection, or introduce a functional barrier preventing migration from the base coat. They are strong, flexible, and usually show excellent adhesion and offer superior retort resistance. Epoxy can coatings can also offer several other advantages, such as universal applicability, high stability, good processability, and low cost. With coil coating epoxy resins, the evolution from a batch process to a continuous assembly line process help manufacturers deliver high-quality, durable finishes with even smoothness. Coil coating involves applying the coating to the metal coil prior to cutting or forming, resulting in a well-bounded and firmly adhered finishes. Dense and tight cross-linking help even out all the flaws like holes or depressions on the metal surface, allowing the formulation for the final top coat to be flawless. Epoxy gives excellent corrosion resistance when used as a primer coat. When used as a back coat, it gives a very good foam adhesion to the insulating PU foam. Coil coating usually cuts down waste, saves time, thereby saving cost and minimizing ecological footprint. Liquid epoxy resins include bisphenol liquid epoxy resins and cycloaliphatic or aliphatic glycol epoxy resins. Like other epoxies, the curing of liquid epoxy resin is fundamental to its commercial use. The EEWs of these resins are smaller than the EEWs of solid epoxy resins, often under 200 gram per equivalent. This indicates that these resins are more active than the other ones. Their viscosity is dependent on their type and can be in the range of 14,000 millipascal per second at 25 centigrade. They may show a tendency for crystallization also. However, liquid epoxy resins, because of their structural and the method of their cure, are superior to other resins in the following properties. They show no volatile loss during the cure of the product. They show dimensional stability during cure, In fact, they exhibit less shrinkage and can be used for very accurate reproduction. They possess good resistance to a variety of chemicals, including solvents, acids, and bases, resulting from properly cured formulations. They have chemicals inertness. They accept a wide range of fillers and pigments. They do not affect encapsulated parts or common containers. Another factor is their durability. Cured formulation exhibit good hardness, impact strength, and toughness. They show great adhesion. The tendency of epoxy adhesion to almost any surface is without equal among organic coatings. Finally, they have versatility in curing agent choice and curing conditions. In the liquid product family, we can name bisphenol A-type epoxy resins, unmodified or modified bisphenol F-type epoxy resins, Phenol-Novolac type epoxy resins, bisphenol A-Novolac type epoxy resins, multifunctional and specialty modified blends, and cycloaliphatic epoxy resins. Solvent-cut epoxy resins have been excluded from this list and will be discussed in the next slides under the name of solution epoxy resins. BPA-type epoxy resins are unmodified bisphenol A-based diglycidyl ethers which usually exhibit very good mechanical, adhesive, dielectric, anti-corrosion, and chemical resistive properties when combined with appropriating curing agents. These resins are widely used as protective coatings, adhesives, construction and civil engineering, marine and underwater, electrical and electronics, and composite applications. Their EEW is in the range of almost 150 to 200 gram per equivalent, and their typical viscosity is in the range of 7,000 to 14,000 millipascal second at 25 centigrade. Bisphenol F-type epoxy resins usually have excellent chemical resistance and chemically resistant. They have a lower viscosity compared to BPA resins. They possess minimum VOCs while achieving the same properties. When formulated well with bisphenol A resins, they usually reduce crystallization tendency. Most pure liquid bisphenol F-based and bisphenol A-F blends resins offer varying viscosities suitable for several applications in adhesives, laminates, electronics, coatings, automotives, pipelines, composites, and civil engineering. Their EEW is often lower than the EEW of bisphenol A-type epoxies and could be in the range of 160 to 180 gram per equivalent. Their viscosity is generally lower than that of BPA. However, they can be provided with viscosities in range of 2,000 to 15,000 millipascal second at 25 centigrade. The other class of this family is high functional epoxy resins of Phenol-Novolac type. Typically, epoxy Phenol-Novolac EPN resins offer a range of varying functionalities. Most of these epoxy resins offer superior temperature and chemical resistance and excellent insulation, making them ideal protective coatings in chemically and thermally hostile environments. They are preferred for applications like high temperature resistant adhesives, corrosion resistant coatings, and floorings, industrial maintenance paint, chemical resistant coatings and linings, potting and casting, and composites. Due to the presence of phenol, their color is yellowish and could be up to 3 gardeners. The EEW is in the range of 150 to 185 gram per equivalent. And their viscosity is much dependent on the type of the resin. It would be in the range of 1,000 to 50,000 millipascal second at 25 centigrade. We also have BPA-Novolac high functionality epoxy resin with EEW of 220 gram per equivalent. These are bisphenol A based Novolac resins, which usually offer superior thermal stability and chemical resistance. Most of these epoxy resins are ideal for use in temperature resistant adhesives, corrosion resistant coatings, industrial maintenance paints, chemical resistant coatings and linings, electrical laminates, molding, tooling, and casting. In this category, usually blends of BPA and BPF resins and reactive diluents, especially Specialty liquid resins can be placed with which offer superior performance compared to BPA-based epoxy resins. They usually reduce viscosity while retaining chemical and solvent resistance. Performance features like chemical and crystallization resistance, thermal stability, high Thg modulus cure speed, and UV resistance are far superior. Especially blends of bio-based resins and amine epoxy are used for composite materials to overcome limitations with typical resins. Specialty liquid resins are mostly used for demanding application in construction, coatings, electrical and electronics, high-performance structural adhesives, and prepregs. These resins have been modified for special features and provide a wide range of EEW and viscosity, which is dependent on the type of resin. We also have multifunctional liquid epoxy resins here, comprising Novolac resins with varying functionalities and tri- and tetrafunctional glycidyl amines. Multifunctional epoxy resins are recommended for demanding application like aerospace, defense, and automotive. With a high Tg, they deliver composites that retain mechanical performance at elevated temperatures. Optimum mix viscosity and long working times, always processing at wide ranging of temperatures. Most multifunctional epoxy resins are suitable for diverse manufacturing technologies like filament binding, pultrusion, wet layup, RTM, and compression molding. The EEW of multifunctional epoxy resins is in the range of 90 to 120 gram per equivalent. The viscosity is also can be low as 500 millipascal second at 25 centigrade. Finally, we have cycloaliphatic epoxy resins, which offer superior durability when exposed to UV radiation when cured with cycloaliphatic curing agents compared to standard bisphenol A type resins. Cycloaliphatic epoxy resins are highly recommended for outdoor coatings, floorings, electrical castings, insulation in castings. They can be provided relatively low viscosities, for example 500 to 3000 millipascal second at 25 centigrade, and they could be based on hexahydrophthalic anhydride, hydrogenated bisphenol A, etc. to endure higher UV resistance. Solution epoxy resins are solvent-cut solid or semi-solid epoxy resins. These are often unmodified BPA-based type epoxies. Generally speaking, these are solvent-cut bisphenol A based on the glycidyl ethers in xylene or other solvents. The solvent has been incorporated to reduce the viscosity and enhance the wearing, which subsequently increases the ease of processing. They mostly offer faster drying and longer pot life compared to standard liquid epoxy resins. Most solvent-cut solid semi-solid epoxy resins are used in solvent-based protective coatings, anti-corrosive marine paintings and varnishes, adhesives, construction, encapsulation, insulation, laminates, tank lining, and primers. These resins have been formulated with a variety of curing agents to suit a specific application. These resins offer good corrosion resistance and excellent adhesion, ideal for primers, high solid systems, finish coats, etc. The portion of the solvent in the resin can be in the range of 10 to 13%. As the solvent does not interfere with the curing processes, the addition of solvent reduces the cross-linking density. Due to the presence of solvent and based on the density of the solvent, the final density of the product would be lower than the other epoxy resins. If a flammable solvent is used for the viscosity cut, the final flash point would be near 25 centigrade and the whole product would be considered as flammable. The carrier solvent could be MEK, xylene, diacetone, alcohol, butanol, methylenamyl ketone, propyl acetate, or etc. These solution resins find usage in solvent-based protective coatings, marine paintings, and varnishes. Xylene is the most common one. Of the advantages of this system, we can imply their faster drying rates and also their longer pot life compared to conventional liquid epoxy resins.
Thanks for your attention. I hope you enjoyed the video. Please share your thoughts, comments, or question, and I will come back to you soon. Thank you.